Hello ladies and gentlemen, and welcome to the 7th game physics tutorial video, and today we are going over collision detection in probably the last video tutorial for this year. Technically PDEs are number 8 I think, but they got recorded a bit earlier, so they should already be uploaded. I think they got released with the 2D rigid bodies a bit earlier because they already were shown in the lecture at the same time. Anyways, let's go and start with collision detections. One of the smaller topics, and some of that should already be familiar to you if you had EIGE already, and if not, well, I think you kind of have to have that because it's in the first semester, unless you're taking this in the first semester as well. But yeah, there are two collision detection phases, the broad phase, which we are going to focus on, and the narrow phase. In the broad phase, the engine or the physics system kind of compares which pairs of object could even be in the danger of colliding at all. And the goal is to throw out any object pairs that could never have any possible collision at all. If there's one object on this side of the screen and one object on the entire opposite of the scene, for example, or yeah, they could not even come close to colliding. And the narrow phase is, which is basically determines finding out what is really colliding, if it could potentially collide, and how and where it collides, and create a collision normal to react to collision properly with forces and everything. But we are mostly focusing on the broad phase because, well, that's the more interesting part for us. Because, yeah. Okay, let's start with one of the certain ways how we could do collision, and that is with bounding volumes. And basically, in this thing, we have simpler geometric shapes, so-called bounding volumes, around our more complex geometrical shapes. And these collision is determined by only these bounding boxes or volumes. And this way we save a lot of time by trying to not calculate the collisions for super complex objects, because more polygons means more checking of collisions, and with the simple things we can approximate it often very well. For different cases we use different volumes here. For example, we have the bounding spheres, which is kind of like a sphere with a radius from the center of mass to the farthest away point, or sometimes a bit further or a bit smaller depending on your use case. Then we have axis aligned bounding boxes. These are just boxes around them, but the edges of them are aligned with the x-axis or the y-axis, and that's why they're called axis aligned bounding boxes. In comparison, we have the orientated bounding boxes, which basically try to find a box shape which has the smallest kind of fit to the object, but they do not have to be aligned with the axes. This way they are sometimes a bit harder to calculate the collisions for, but a lot more accurate, obviously, because you see the shape of this blue box is a lot more accurate to the real shape, or more close matching than, for example, this axis aligned bounding box is with the shape here. Then we have discrete oriented polytypes, which are basically a bit more close approximations of the bounding volume to the actual object, with a bit more polygons or edges here than a simple box. And then we have convex hulls, which are basically, we use they are the more complex and more detailed ones. We basically use the complete shape of the object itself, but if there's any concave little indents, we kind of bridge these with a convex hull. That's why they're called convex hulls. Okay, the first broad phase algorithm or method we're looking at is the so-called bounding hierarchies. We kind of built a tree or a hierarchy of bounding volumes with bigger ones including smaller ones, and then it allows us to terminate early high-level bounding volumes that cannot overlap at all. And then if we detect an overlap between some, we go closer into a bit more deeper into the tree or the hierarchy to find the closer matching bounding volumes and throw out more and more polygons until we actually only have the smallest bounding volumes, and then we go down to the polygon level or actual collision level, collision detection, and we save us a lot of triangle we don't have to compare. Okay, so here we are. We have two triangle strips here that would collide here. So we have two big, in the first phase of the hierarchy, we have two big collision bounding boxes, bounding volumes. They're not boxes, they're more like spheres here. So bounding volumes, we detected they collide. So we go one step deeper. In this further step, we see, oh yes, these outer two leaves of these big boxes, they can't even collide at all, doesn't work. Then we only check the smaller ones. These split up into two even smaller ones, and we check again, oh yeah, the further away ones, they don't even intersect at all. They cannot collide, but the ones in the middle could. And then we highlight, or we are the furthest down the tree or the hierarchy, and we go down to the actual polygons, the triangles, and we see, okay, these are in these smallest bounding volumes. Let's highlight them all, and then we do a concrete detailed test of which triangles actually overlap. And that way we saved a lot of tests between each and every one of the outest, which could not collide at all in a logical sense, but a naive implementation of an algorithm that only checks for collisions wouldn't know that. So yeah. Then we have another broad phase way of detecting, which can be, or well, it can be used together with those. A lot of those can be used in conjunction and in commercial game engines and good physics systems. Basically, all of this is implemented in some way or another, probably a lot more performant than these simple things we look at here today, but they're built kind of the basis of what modern collision detection systems and physics systems are built upon. Okay, then we have the sweep and prune feed or broad phase algorithm or method. For this we use axis-aligned bounding boxes. If you remember, AABBs are axis-aligned bounding boxes, and they kind of try to find a box that fits the shape, but the edges of the boxes have to be aligned with the x and the y axes. And then we project these boxes onto a coordinate axis, basically like a timeline. We only look at the x and the y. In a 2D system, we could do a Z in a 3D system, and then we kind of open an interval here like a bracket and close it when one particular bounding box is ended. So for example, here we open it here and close it here, but whenever we detect that a interval opens for the one before it closed, we detect a collision. So here we start with this little S shape. We open the interval for the S shape on the x-axis projected, and then we, in our prune and sweep, or sweep and prune, we detect another opening of the next interval for the little circle here. And this way we know we collided because there's two opening intervals right next to each other, right after each other, before the first interval could close, which closes slightly after, and we collect the division between the S and the circle. And here we have the N opens, then the triangle here opens before the N could close, and we know again two open intervals at the same time means we have a collision. And we can throw out all pairs which basically have no collisions by seeing if they open and close without any interference whatsoever. Then we go back to the next one, which is spatial partitioning. You basically try to split any 2D view, it's mostly two-dimensional views, into, you take like a snapshot from any axis basically in a 3D system, or in a 2D system it's just the normal view, and you try to partition it into certain spaces. And there's different ways to do this with a uniform grid, which is just a grid like in any grid-based system. Then we have quad trees or octrees, which basically go smaller and smaller depending on where more objects are. So if there's a lot of objects in this part of our 2D gameplay area, for example, we would have a lot more partitionings here. And if there's only one object here, and we know that, we don't need to partition it any further because we know there's only one object there. Why would we put any effort into partitioning further if it can't possibly collide with anything? And then we have a KD tree, which kind of does a similar thing, but it is much more free in where to add extra partitionings. Here we can only do equal partitionings in smaller, like in an equal fashion. So we can only half, in a quad-tree, oct-tree system, we can only half squares we created before. And here we can create them a bit more freely, but still aligned to the axis. And the BSP tree kind of can partition everything according to any wild lines or vectors in any system. In the 3D system, they could be completely 3D vectors, free space. They do not have to be aligned to anything. And then we kind of number or kind of analyze each cell, and we see which objects are at which cell, and only objects that share a cell. So if in one cell there's two objects, they even have a risk of colliding, and only then we start other or more refined collision detection schemes or phases, algorithms, to check if they actually collide. Because if, for example, there would be an object here and an object here, we know they are in different sections and different partitions, and they run in no way a risk of colliding. And we update this, of course, whenever an object moves or rotates. Okay. Yes, exactly. We split everything the same size. Here we have an even grid, but an increased resolution where there are more objects. Split grid along every axis, 8 new cells, and so on and so forth. And then we split everything according to X and Y axes, but kind of wherever we want. And the BSB tree here is kind of, a bit more unique. We can pick basically any vector or any axis. We split along an arbitrary axis. Maybe a plane of a polygon is kind of a recommended thing. And then, for example, we split it, the whole thing, at this A axis here. And then we created a tree. So we split at A, and all parts that are above it are left or right. It's really arbitrary way I said it. And the other ones are on the other leaf of the tree. And then we could, for example, split these leaves even further by using this B2 here, split it along B2, and categorize them even further into, well, smaller leaves to get a more precise scheme. Okay, let's start with the exercises. They are a bit more simple than big calculation exercises. So for this, I'm probably not going to use OneNote and take any notes. I'm just going to quickly go over them, explain why it is, and then show you the solutions. You can pause the video at any time and kind of take a screen cap and draw the lines and do the little calculations you have to do here yourself if you want. And you should do, they're important. This is stuff that has and could very well be in the exam. In my exam, we had something similar to, I think, the next exercise after this one. And yeah, you should know these. These can potentially give quite a lot of points if you're a bit lucky, because I think they're pretty okay to do, pretty easy to manage. Anyways, let's start. So using a grid with spacing 1 as an acceleration structure, list all pairs of objects, e.g. AD, that need to be checked during the narrow phase. Okay, the keyword we have here is a grid. If we remember back to a couple of minutes ago, we have this uniform grid scheme, and we have to kind of mark all the pairs. So we kind of go step by step and check which grid has 2 objects in it, and then we list them as pairs because they need to be checked. So here we have no collisions until now, and we go in here and here and here, and this square, we see we have E and B, so we mark down E and B as one possible combination, and we go down, nothing, 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 nothing. And here we again have C and B, and the next one is C and B again. just note that down as one pair. We just have to note down all the pairs of objects that could potentially collide and need to be checked out in another phase. So for now we have E and B and B and C. And then we have check, 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 check. Oh, here we have one, G and F also need to be checked. Mark down G and F, and then we should be done. No more collisions. I mean, if you want to be a bit cheaty, just look at all the objects you can clearly see that could collide. But, you know, if you look at that and you don't actually do it step by step, you might miss stuff like this one, the E and B one, because they don't clearly look like they collide or could collide. E and B don't look like they would collide for the human eye, but for the broad phase algorithm, it would flag them as could potentially collide, check and error phase. So mark them down. Okay, yeah, EB, BC, FG, we got this. Good one. Next one. Which objects will be stored in which leaves in the given KT tree? Okay, so we remember back KT tree, this one, axis aligned partitions, kind of partition walls, but yeah, they can be kind of everywhere. Okay, so let's check. We have x equals 4. So if we have x equals 4, we kind of go to the x-axis, check it 4. Okay, 4. And then we kind of draw a line upwards from there. Or if it were like, for example, here we have y equals 3, go on the y-axis to 3 and draw a line leftwards. So okay, we start with x equals 4. So we kind of imagine a line here. We have to keep that in mind for now, because if I skip to the next page, the line will be in, but you will have the solution. So kind of draw that yourself. I don't know, maybe in a note-taking tool or something. And then we check everything on the left of that and everything to the right of that. So to the left of that, I'm presuming everything here is to the left of that and everything here is to the right of that. Same as I'm assuming everything to the left of a Y node or a Y KD tree wall is above the line and everything to the right of it is below the line. It's kind of the standard they set in these exercises here, I think. But honestly, if you do it the other way around and do it consistently that way, nobody's probably going to blame you. But I mean, keep it the way I just told you and you'll be on the safe side. Anyways, we draw a line at 4 and then we only check the stuff on the left, and we further divide the left with a line called y equals 3. So we draw a line here until 4. Okay, so everything on this left here would be above it. So left of 4 and above 3, that gives us a little square here if we draw it like that. And in this little thing, in this little square, we would have, or in this little box, it's not really a square, we would have F kind of intersects it, is in it, partially E is kind of in it, and A is kind of in it. So down here we would write E, A, and F. Then we have Y equals 3, so below that, but still left of the, below 3, but still left of the 4, we have kind of a little box here, and we have F and G in it, so write down F and G here. And then we go back here to the right of the 4, and we draw a new line, which is Y equals 4. So kind of here. And then again above it, we have a little box in which we have E. Part of E is still in it, so we mark down E, even though it has been another box before. And then B as well, so E and B we have here. And then in the lower part here, we have B and C. And D as well. Yes, D as well. So let's check if that's correct. G and F. Okay, the left one is actually below and the right one of the Y coordinate is above. Okay, it's a bit different. So we have GF down here. We have AEF on top. Okay, BCD down here and BE up here. But that's pretty understandable. Otherwise, go to the weekly sessions we have. Okay, let's continue with the next exercise, C. How do we need to choose the axis subdivisions if no object should appear in more than one leaf and no leaf should have more than 3 entries? Okay, so for this, that's kind of a bit different. We kind of need to draw our own lines, basically do it like that. Don't try to imagine like y and x or something. Just try drawing lines to partition everything into little boxes that fulfill the criteria we have here. Okay, no object should appear in more than one leaf, and no leaf should have more than 3 entries. Okay, for that we basically have to kind of, for the first, no object should appear in more than one leaf. For that we kind of have to draw partitionings that don't intersect anything. As soon as we intersect anything with a line, we have one object in more than one leaf. So the only way to really do this is, let's start with the X because it's easier. I think it's the only actually possible one, because it's the only one that goes straight through. Kind of, if you want to have to pick the first one, just draw a line straight through from the beginning to the end and see if it kind of fits. In here we don't have any of that. We could go at the very top or the very bottom, but I mean, then we would probably violate the second one with the 3 entries. So yeah, we can't kind of shoot a ray down here in this direction and not intersect anything or cut through anything. So we start with 3 and go up here. So the first one we probably write or note this down. It's not yet the given solution, but we can probably write that down already since it's the only option. So write down x equals 3 because we have a line from the x-axis up, x equals 3. And then, well, the only other two from here on the left side we can shoot up is kind of this line without intersecting. Again, we could probably put it down here or up here, but that would kind of defeat the purpose because, you know, it's kind of meant to separate things that cannot possibly collide. So yeah, let's draw the line here. So on the left side we have y equals 4 because we have y position 4, and this line only goes up to this middle line of 3 we kind of defined in here, and so it doesn't cut through here, so it doesn't violate our first criterion. And then on the other side, on the right side, the only thing we can do is shoot a line from y equals 2. Obviously we are on the right side of the 3, so we start up here. So we should have x equals 3 here, y equals 4 here, and y equals 2 on the other side. And I think we are correct with the lines already drawn in. I hope that helped you, and you probably got that yourself. But I think this was, in my exam, one of the things that was asked, and it got me quite a lot of points, so it's a good thing to notice. Let's continue. There's a big one other thing we missed before or didn't go over before in the separating axis test things, and that is the big separating axis test thing. Yeah, so we can kind of take these trees, but we can also find an axis in which two things do not overlap to see if they are not colliding. So for any given two objects in a space, if we can find one axis and then like kind of project them on this axis and they do not collide on this axis, or they do not overlap on this axis, on this projection of the axis, on the axis, we know they do not overlap. We just only have to find one of those. And well, which axis do we test on? And we normally try all of the normals of the polygon edges to find an axis. This is kind of thing that's done, and it's often quite a good way to test things. It is a bit more, well, calculation heavy, resource heavy than, I don't know, for example, a spatial partitioning test, but it's also more precise. And the SAT gives us also a direction along which we should push the objects apart. So if there's an axis with at least an overlap that is greater than 0, we can use this axis as our collision normal for impulse calculation. So it's also not only a broad phase algorithm, but if you detect a collision here, you could also use this normal as a collision normal for a broad phase algorithm or physics calculation to calculate actually how the objects react after they collided. Okay, so let's try a couple of exercises here. We have an 2D area here, and we have two triangles T1 and T2, and we are supposed to govern or say what the intervals are required for an SAT test along the axis n equals 1, 0. And we have a little hint, the length along an axis you want to project on is just the dot product of the coordinates on that axis. And I'm going to actually show you the solution before we do the calculations, because they're a bit too simple to open OneNote for them. But I kind of want to show you what we're doing without just talking without any numbers here, because it's a bit more complex than the things above. But before that, when you have such a test or such an exercise before you, always look at this axis at which you're supposed to project. Very often, those are simple axes, or often they could be. So for example, n1, 0, so 1 in the x direction, 0 in the y direction is just the x-axis. And if you look at something on the x-axis, if they collide, that's really easy to see. You can see that by eye, they would collide. And the intervals we need to test here would be from the extremes here, so from the biggest x-axis coordinate here to the biggest x-axis coordinate here. So now from the smallest of the first triangle to the biggest of the first triangle, so 2 and 5 would be one interval. And then from the smallest of the second triangle to the largest of the second triangle, so from 4 to 6 in the x-axis direction would be the interval for the second one. And then we need a third one, which is basically from the smallest position of the whole thing, so 2 in this case and 6 in this case. In this case, you wouldn't even have to do a dot product at all, and you could just read the intervals right from the sheet. So always look at the axes. They can potentially save you a lot of time. So yeah, here project each point onto the axes. For what you do is you kind of do a dot product of the point you want to check. So you do this for every point here. And the normal or the axis on which you want to project it on. So x1 is this point, x2 is probably this point, x3 is probably this point. Yes, exactly. And then we normal is, or the n, the axis is 1, 0, and then we get 2, 3, 5, 4, 5, 6. And then for the, if they ask you for the free intervals in a separating axis test in 2D, what you do is the first interval is the biggest of the first triangle minus the smallest of the first triangle. So basically we look at the free dot product we get in a triangle. It would be 4 in a cube, not in a cube, in a box, and 5 in a pentagram, for example, but or in a pentagon, I think it's called, a pentagram. And even more if you have more edges, but you just look at, you do all those dot products for every point and the axis you want to test on, and you look at and you kind of separate them for each object you have, and then you look for the smallest one, in this case 2, and the biggest one, in this case 5, so 5 and 2, and then the length you get by using the maximum subtracted minus the minimum, and then you do that for the second one here too. So the dot product here we have 4, 5, and 6, so we have 6 minus 4, maximum minus minimum, length 2, and then to get the third one or fourth one, if we have 3 objects, basically the last one is always the biggest number in total minus the smallest number in total, or from the smallest, the interval from the smallest one to the biggest one. So for example, we look for all values here, 2, 3, 5, 4, 5, 6. The smallest one will be 2, and the biggest one is 6. So 6 minus 2 is length equals 4. Good. I hope that was clear. And then this one is a bit more complicated. Given the triangles T1 and T2, what are the 3 intervals required for SAT along the axis m equals 1, 2? So the axis would be something like this. We would draw it, and it's a bit harder to guess the exact numbers, and well, it's kind of still okay to imagine a 3D space. It would get a bit more complicated. But it's, especially if we have like this axis, would they collide or not collide? We kind of couldn't see it, because, you know, on the x-axis we could clearly see that they would collide, but on an axis 1, 2, we can't quite see it. They could just not quite collide on this axis, and they probably don't, because we know from a 3D view they don't collide. And as you have heard before, we need to just find one axis that doesn't collide. There's no interval that overlaps here to prove that they are not actually colliding. Okay, let's look at the numbers again, because I don't want to do the dot products myself. So the dot product with 2, 2 for the first point and m 1, 2 gives us 6. For 3, 4 with 1, 2 gives us 11, and 5, 2.5 and 1, 2 gives us 10. And we do the second one for all the points in the second triangle, 11, 11, 18. And then again, the first interval we have is the biggest one of the maximum of the first one, so 11. And in this time, and 6 is the smallest one, so 11 and 6, the length is 5. And then here we look for the biggest one again, 18, and the smallest one, which is twice 11. Okay, so they are probably like right on top of each other. Yes, so we can use any one of those. It doesn't really matter. We just use the number 11. So we have 18 and 11. It's the length of 7, and then we go through all of them again. So 6, 11, 10, 11, 11, 18. The biggest one is 18, and the smallest one should be 6. So 18 minus 6, length equals 12. Okay, we have those 3 intervals for 2 objects in any space. How do we actually know if they collide or if they don't collide? Well, how would you do this? Pause the video and ask yourself that. How could we, with the simplest calculation, without having, like sometimes one object is from 2 to 5 and the other one is from 10,000 to 10,005. How can we very easily, for example, compare those two if we don't want to deal with big numbers, for example? I'll pause here if you want to ask yourself, but I'm going to jump to the solution now. The solution is if the whole interval is larger than the sum of the intervals, the axis is separating. When it's less, it's intersecting. Equal is touching, and a single separating axis is found, then we have no intersection between the shapes, as I said. So for the first test, we would say the length of the whole interval is 4, and the sum of all the partial intervals is 2 and 3, so 5. And we know 5 is longer than 4, so we know on the x-axis, or the axis 1, 0, they are intersecting. And then on the second separating axis test, we have the 2 intervals 5 and 7, which are 5 plus 7 is 12, and we have the length 12. So we know they are the same, the interval length is the same, and that way we know they are touching, but not intersecting. And we could probably find another axis here, as you can see, which goes like kind of perpendicular to the axis that to the line that kind of crosses between them, and from that one, or one that's basically parallel to this line here but a bit more out, if we put one perpendicular to that one, we had an axis where the full interval would be larger than the sum of the partial intervals, and then we would know they're not actually intersecting because we found a single separating axis. That's it for the broad face. We now go on to the narrow face. And well, once the broad face is over, we are left with a small number of pairs of objects which we actually need to check for collision in detail. And these tests heavily depend on the objects we're trying to compare. If we have spheres, if the spheres have sphere colliders, or if we have like, we are in a different graphical calculation phase where we kind of want to check the formation and need to actually check the meshes and not the box colliders we made for them and something like that. And basically there's already established specialized intersection algorithms for pretty much any case and edge case you can find out there. They're already defined and in use in pretty much any big physics system, and any big game engine that has one of those physics systems. For example, the new chaos physics system for the Unreal Engine has probably hundreds of those for any kind of object, and kind of intelligently chooses which one to use. And yeah, line intersecting a plane, you probably know that from school. I don't quite remember the details for that, for example. as well. I kind of had to probably look them up or think about them for a while to get them fully into my brain. And basically, these algorithms also need to give us collision points, collision normals, collision depth, and even more information for some more complicated systems, if you want that. And as it's written here, these little comments are really the real MVP of this whole lecture or this whole tutorial. They tell us the narrow phase is not really part of this lecture, since it's mainly looking up the algorithm for each specific case. So kind of know what the narrow phase is, what it does. You probably already know that. And know what it needs to provide to you. This might be like part of some multiple choice test at the beginning of the exam or something, but there's actually no specific narrow phase algorithms you need to know. And with that, thanks for attending, or rather listening on YouTube. I hope these could help you. I hope these prepared you sufficiently for the exam. I had a good blast recording them, even though my PC kind of died in the middle of everything as well. But I hope they helped you from the response I got. And Annalena told me they were received quite well, so I hope maybe we can keep them for next year. Please, please, please give us feedback on Moodle, on my Discord. Write me feedback. Just write us a mail. Anything would help. If there's anything you didn't like, if you found a mistake we made in these videos, we can still fix them, and then maybe we can help other people in the next years with that. And if you didn't understand anything, as always, email, Discord. But first check live back with us in the live exercises or Q&A sessions we do every Monday, Tuesday, Wednesday, Thursday. I'm on Monday and Wednesday, and Annalena is on Tuesday and Thursday. Check with us there. We do not only answer programming questions there, we also answer like slide questions, and we are there live, so it's better experience and easier for us to answer. And other than that, thanks for attending. Wish you a good evening, night, day, whatever it is, and good luck in the exam.